Okay. If you're watching this talk, you probably know Frank from his work on Libsodium. But before that, Frank was and is a photographer. And I think I'm not saying anything surprising by pointing out that to be a photographer, you need to have a mind particularly sensitive to elegance and beauty, which maybe explains his interest in crypto, and which definitely explains his interest in Zig. So, the title is a tour of std.crypto in Zig 0.7.0. Frank, the stream is yours.
Hello, everyone. So, hope you're as excited as I am about the forthcoming release of Zig 0.7.0. There's been so many changes. I haven't been able to keep up with all the changes. So really have been focused on just one thing, which is the std crypto directory. I've been somehow able to follow that one. So this is what we're going to talk about today. So what is std.crypto? What can you find in here?
Frank, sorry to interrupt you.
Essentially, yeah.
I think we need to restart the video stream. For some reason, it's all black.
Oh, okay.
Give me a second. I'll try to do it. Okay, now it works. Now we see the title. Zig for cryptography.
Okay.
std crypto.
And
okay, sorry.
Next slide
yes,
as well?
Now it's working. Yeah. Apologies.
Oh, okay. Perfect. Anyway, you didn't miss anything important. So std.crypto, what is it? What can we find? Well, crypto APIs. Crypto APIs doesn't mean anything because, if you take a look around, look at existing crypto APIs, there are many, many kind of APIs you can find. For example, some of them, right in the middle, provide constructions and primitives, things for hashing or encryption, signatures. This is probably the most common kind of crypto libraries, and so APIs that you can find. But also, on top of this kind of APIs, you can find protocols. And when I say protocols, this is not just network protocols. It could be a file format to encrypt files. It could be TLS. It could be a specific blockchain. So all these high-level APIs are built on top of what's in the middle, on top of constructions and primitives. So different set of APIs. And at the very bottom, we have a bunch of foundations, such as being able to do finite field arithmetic or even hardware abstractions. Still a different kind of APIs. So where do we stand? What do we have in Zig? Well, let's take a look at what we actually have in std.crypto. Since Zig 0.7, everything has been organized into a bunch of categories. So we can take a look at one of them, which is core. And core is pretty interesting because if you just use it alone, it's pretty much useless. So let's take a look. For example, you're going to find things such as AES, Gimli, and mods. So AES may sound familiar. So let's take a look at AES. What is AES, by the way? AES is just a permutation. So you take a set of numbers, actually a list. This is what you have on the left. And you just shuffle that list in a pretty messy way. You get the list on the right. And AES is pretty much this kind of map function that maps what's on the left to what you get on the right. And if you perform exactly the same steps, but in reverse, you can go from the right back to the left. This is a permutation. And AES is pretty much exactly that, except that instead of having just 10 elements, you have a little bit more. We have blocks of 128 bits. So that's bigger, but it's still deterministic. You can go from the left to the right and the other way around. This is all what the AES core function does, nothing else. So AES was really designed for hardware implementations. If you try to implement AES in software, it may be insecure due to side channels. And if you want to implement mitigations against side channels, Well, they have a cost, and then it's going to be slow. This is not great, right? So what can we do? Well, modern CPUs have dedicated instruction sets for AES. For example, on Intel, we have the ASNI instruction set, and on ARM CPUs, we have ARM crypto extensions, which provide a bunch of interesting things, including AES functions. So great. However, this requires using intrinsics or assembly code. Even in Zig, this is not something we can do directly. Plus, even if these instructions look similar, they're not really the same. They have to be used differently to achieve the same result. So it's a little bit annoying if you want something portable and easy to use. Anyway, so if you use hardware instructions for AES, maybe you're going to be fast and secure. Well, not quite. Let me tell you why. Well, you could go way faster, actually, because modern CPUs are fast, if only because they have executions pipelines. They can start processing an instruction before the previous one is even done. So if we take a look at the AES instruction, this is on Intel. AES Enc just encrypts an AES block. And on this specific CPU, this instruction has a latency of 4 clock cycles, which means that when you start this instruction, it's going to take 4 cycles before you get the result. So you can compute whatever you need to provide to this instruction, run it, get what you need for the next round, and do it again and again in a very sequential way. Or what you can do is prepare everything for a couple calls of this instruction, and then performs many calls in a row. So on this CPU, we have a latency of 4, but a throughput of 1, which means that we can schedule a new one, just one cycle after the previous one, even if the previous one is not done yet. So, and you can see here, if we do 4 AES encryption instead of 1, and then another one, and then another one, and then another one, it's way faster. So having a multiple of 4 blocks sounds pretty nice, quite faster. So parallelism is important. And on that CPU, which is AMD Zen and Zen 2, we actually have 2 execution pipelines. So we probably should run 8 AES encryption at the same time to get optimal throughput. So it's nice, but it's very hardware specific. For example, here I've been talking about 2 execution pipelines. So 8 is a nice number to choose for parallelism, but is it some kind of magic number that works everywhere? Well, not quite. If you take a look at the Zig source code, you're going to see something like this. We actually exposed the optimal number of blocks to use for different models of CPUs. This list is not extensive, but still, it's useful. Also, we have a parallel version of the AES API, so you can send a vector, and it's going to do AES encryption as fast as possible by leveraging parallelism. So, cool. This is something we can do easily in Zig. What can we do with that? Well, imagine you have a secret. We run this AES function, and then we get the secret encrypted. Sounds easy, right? Well, just to be sure, to be really secure, we can run this AES function a couple times. There's an intuition that if we run it more than once, it might be more secure, and it actually is. However, remember that AES is a permutation, and a permutation can be reversed. You can execute the same steps in reverse, and even if you have 1 million iterations of this AES function, this scheme is completely insecure. It doesn't provide any kind of security whatsoever, even if it says AES. All right. So this is something we can fix. For example, instead of having our secrets directly on the top, what we can do is expand this secret into multiple secrets. And then we add these secrets. So this weird symbol in the middle of each arrows is technically an addition. You can see that as XOR in practice. So we just mix a secret or a part of the secret between each round of the AES function. Why do we do that? Well, if you start from the bottom and your goal is to go up to the initial secret or to recover all the secrets, well, you can try to go up, but if you don't know secret underscore 5 here, when you reverse the permutation, all you're gonna get is something that doesn't make any sense, and this is not the real output of the previous iteration. So having this intermediate secret is what makes the scheme actually secure. And the higher you have to get, the more secure you will be. This is a more realistic way to use AES, because with the previous scheme, we were able to encrypt a secret, and that's it. In practice, what you usually want to do is have a key and then use that key to encrypt multiple things. So we do pretty much exactly the same thing as on the previous slide. We start from the key, we expand this key into multiple subkeys. They are called round keys. And we don't have 5 of them. In practice, we have between 10 and 14 of them. And we do exactly the same thing as before. We add each round key between each round. So what do we have at the top? Well, I just wrote something, because it could be anything. It could be a secret message that you want to encrypt, or it could be something absolutely not secret. But no matter what you have, at the end, at the very bottom, what you're gonna get is deterministic gibberish. It looks like completely random. However, if you know the key for a given something and a given key, it's gonna be exactly the same thing every time. So what we just built right here is called a block cipher. And having to apply each key between each round, it's called a key schedule. If you take a look at the Zig source code, you're gonna see a type called key schedule. And this type is able to compute all the intermediate round key that you can see here. And if you want to do this whole thing, do the key expansion and then run multiple rounds, and then you get this gibberish, you have 2 very simple functions, AES encrypt and AES decrypt. The second one does exactly the same thing, just in reverse. Very cool. However, so far, what we can do is encrypt 16 bytes. I mean, it's okay. It's not too bad. There is some satisfaction here, but it's a little bit lame. We may want to encrypt more. So what can we do? Well, there are different things we could do, and these things are called mods. One of them is very simple and intuitive. The input, the something that we had, I don't know, 3 slides before, the something can be just a block number. So we're gonna split the message into multiple blocks of 16 bytes. And then the input is gonna be block 1, block number 2, block number 3, just the block number. We're gonna apply exactly the same key schedule every time. But because we have a different input, the output for every single block is going to be completely different. So we're going to get gibberish, but completely different gibberish if we have 1 as an input or if we have 2. So if we combine this gibberish with each message block, we get the message, but encrypted. One pretty nice thing about this scheme is the fact that it's easy to vectorize. Because we use exactly the same key schedule, we can encrypt 4 or 8 or 7 blocks at the same time. And remember that if you process multiple blocks at the same time, it can be faster because you can leverage what modern CPUs can do. So this specific mode is used a lot nowadays because it's fast. So if you want to use a mod, Zig got you covered. You have something in core, because we are looking at core right now, called mods. And in mods, you can find CTR, which implements counter mode. Great. So we can encrypt a message of any length now. Awesome. Are we secure yet? Well, not really. Remember that we got this gibberish, and then we just XOR this gibberish with a message. So an attacker can flip a bit in the ciphertext, and it's going to flip the same bit in the message. And there is no way we can detect that the message has been tampered with. This is slightly annoying. So how to fix that? Introducing MACs. So a MAC, a message authentication code, is a very simple function that takes a message and a key, and it returns a tag, authentication tag. Essentially, if you know the key, you can compute a tag for any message. But also, if you are sent a message and a tag, and you know the key, you can recompute the key and verify that the tag that you got matches the one that you computed. If it's the case, the message hasn't been tampered with. If there's a mismatch, you should just ignore the message. Something wrong happened. And if an attacker doesn't know okay, there's nothing they can do. They can't compute any valid message for the tag, and they can't change the message and compute a valid tag either. So in Zig, MACs are available as crypto.auth.something and also crypto one-time auth. What's the difference, you may ask? Well, in the second case, one-time auth, we are dealing with what's called universal hash functions. These functions can be really fast, and they also have some interesting properties. But the downside is that a key has to be used only once. If you reuse a key with two different messages, an attacker can compute a valid tag for a different message, which kind of defeats the whole purpose of a MAC. So the second category is super interesting, quite fast, quite common, but it can be tricky to use correctly. Change the key every time you want to authenticate a new message. Okay, so far we know how to encrypt a message of any length. Nice. We know how to compute something to detect if a message has been tampered with. We can combine both, and then we get what's called authenticated encryption. This is cool. Now you want to send this to another party. Maybe you want to add some non-secret information. For example, a protocol version, which can be useful to know what kind of cipher has been used to encrypt the message. So this is something you don't want to be encrypted, but this is something also that you don't want a third party to be able to change. For an example of why this is bad, take a look at JWT. This is terrible. You can change the kind of encryption, and there's no way to detect that it happened, and it's catastrophic. Don't get me started on JWT. So what you can do to prevent that is when you compute the tag to include this extra data, this non-encrypted data, in this case, the protocol version in the computation. So this is called either additional data or associated data. You can find both. I tend to say additional, but both are okay. So you compute this tag, which is going to authenticate both the message or the ciphertext that represents the same thing and some non-secret data. And you send everything, this additional data on the clear, the ciphertext, and the tag to some recipient. You just built what's called an ahead. So authenticated encryption with additional data. Awesome. Are we secure yet? Not really. If you send the same message twice, the ciphertext and the tag actually will be exactly the same. And maybe this is not something you want to disclose. And remember that for some MACs, you shouldn't use the same key twice. And that will be the key, the case. So introducing nonces. So a nonce is just a number that you should use only once. And if you encrypt something using a nonce, you get some ciphertext and tag. And if you change the nonce, even just 1 bit, well, you get a completely different ciphertext and tag. So cool, problem solved. Now, if you encrypt the same message twice, you get completely different output. So what can you use as a nonce? A counter might work. It might not repeat too fast. However, you have to keep states, can be tricky. Maybe you can use a random nonce, which can be okay, except that if the size of a nonce is pretty small, you need to switch to a new key before you get a collision. So in some protocols, this is okay. In some other protocols, there's some overhead, and you have more things to design and implement. So the nonce size is an important parameter. Anyway, are we secure yet? Not really, because we should use different keys for authentication and encryption. Well, first, this is good hygiene, and then maybe they must have a different size. So, well, we need something that takes one key and derives two keys out of it. Yeah, that's a lot already. So just some takeaways so far. First, if a product says, hey, it uses AES-256, well, it doesn't mean anything. In particular, it doesn't mean that it's secure. If you don't get any additional information, it's probably snake oil cryptography, especially if it says military grade. So is there a way to do everything we've been discussing so far in a very simple way using standard constructions? Yeah, absolutely. So in Zig, you have something in crypto.ahead. We have actually a bunch of constructions exposing the same set of APIs with two interesting functions, encrypt and decrypt. Encrypt takes a message, additional data, which can be empty, a nonce, a key, and boom, you get the ciphertext and a tag. And decrypt does the opposite operation and verifies that the tag is valid. Cool, much, much, much easier to use, right? Cool, so what do we have in crypto.ahead exactly? We have something called ASGCM. You can use it if compliance is a priority for you. It's a pretty old construction, but it's still okay. Nonces are small, which is okay for TLS because TLS includes everything you need to negotiate a new key over an existing connection. But if you re-implement your own protocol, it can be a little bit lousy to use correctly. ASGCM is fast if you have AES acceleration. So it's fast on recent CPUs, but on non-Intel, non-ARM CPUs without acceleration, it can be slow and or insecure. Cha-Cha-20 Poly 1305. So this is a pretty new construction. If you use TLS 1.3, and you probably do, you are aware of it. So it's a nice construction. It has nonce which can be the same size as AES-GCM, or it could be pretty large. And this is interesting. This is an extended version of this construction, which is being standardized right now. And with this pretty large nonce, you can pick nonces using a random number generator, and you will never ever get a collision, which is super cool. It's also faster than AES-GCM and safer. So if you don't have AES acceleration, it's a good choice. We have a variant called Xsalsa with pretty much the same properties. I'm going to talk about it later. Edges. This is a very new construction. It's been explicitly designed for modern CPUs with ASNI. It's super, super, super fast. So I don't want to spoil it. If you want to have some fun, you can run the benchmark that you can find in std.crypto. It's super fast on Intel, but also on ARM. Even the software implementation is super fast. It's actually more secure than AES-GCM, especially due to the GCM part of AES-GCM, and way faster. Plus, it has a large nonce, a really large nonce if you use the 256 version, which is nice. So you can not only pick nonces at random, but also include additional information in the nonce itself, such as a packet number or whatever. This is a really, really cool cipher. Gimli is very small, lightweight. The performance is not that great, but it's consistent across all platforms. Okay, so where do the Zig crypto APIs fit? So as we just saw right here, we don't provide any kind of high-level protocols, but we provide not only foundations, you have direct access to the AES permutation, for example, but we also provide ready-to-use constructions. Why do we expose low-level APIs? Well, one of the reasons is that you can implement new cryptography easily. You can leverage what we have, such as hardware abstractions, very easily in pure Zig. And this is really nice. If we didn't had edges, for example, this is something we could implement without having to use assembly or whatever. Why don't we implement protocol? The highest level of APIs. Well, most of them are really domain specific. If you want to implement a blockchain or if you want to just do file encryption, you probably don't want the same kind of APIs. Plus, you have to pick specific constructions and file formats and network protocols and encoding formats and what's not. So these things are really opinionated, and this is probably not something that we want to see in the standard library. They are better implemented as external packages. However, we provide all the building blocks so that you can implement these protocols easily and securely. All right, so back to our little tour of std.crypto. Crypto.hash, nothing really surprising here. Hash functions. A hash function takes a message and returns something of a fixed length. If you get a hash, finding a message giving this hash is hard. Finding a different message producing the same hash is hard. Finding a collision is hard too, even for quantum computers. Great. So I just said that a hash function is something that takes a message and return a digest. Well, this
I think we lost Frank. Okay, people in chat, can you confirm that I'm still alive? I should be, I think. I don't see drop frames. Let me see. Yeah, I don't have drop frames, so I think we lost Frank. Okay, let's give him a second to come back. That's the problem of having everyone.
parameters.
Okay, Frank.
Yeah.
Sorry.
Yeah.
You got cut off for like I think 10 to 15 seconds completely. So
Okay.
let me see if the streaming is still alive. Yes. So we lost you briefly when you were saying that hashes have a fixed length, and then you were about to say that that's not good enough, I guess.
Oh, okay. Okay. So I can do it again. No worries.
Sorry.
Okay. So sorry, people. Apparently, we got cut a little bit. No worries. So a hash function being defined as something that takes a message and return a fixed length digest is okay, but it's a little bit of a traditional definition, and it doesn't really match modern hash functions that can do much, much more. For example, modern hash functions can spit out a digest of any length or of a length between some range. In addition to that, modern hash functions can accept an optional key and a context. They can leverage multiple cores, so you can also specify a number of threads, and so on and so forth. And according to the function you use, the set of available parameters can vary. So we need to provide a modern API that adjusts to modern functions. Which is why, and it might be surprising at first, you can see that when you use a hash function in Zig, this initialization function requires a set, which is empty here, but this is a set of parameters. And the actual set of parameters depend on what primitive you choose. For example, for Blake2B here, we could easily add a key, a context, a thought, everything that Blake2 has to offer. This is supported in Zig right now. You just have to pass it as an option. And something important in the Zig crypto APIs is that within the same family of function, the APIs are the same, which is why even for hash functions such as SHA1 or MD5 that don't support parameters, you still have to use an empty set just for consistency. So this is what we have for hash functions. One which is pretty interesting and that you will probably recognize is Gimli. Gimli can be used both for encryption and for hashing. If you want to minimize the memory usage and storage, you can use Gimli for both operations. It's not super fast, but if you're looking for something very small, it's a good choice. Blake 3 is eventually the one who's going to be super, super fast. Right now, it's not as fast as it could be. There's a lot of room for optimizations, but this will eventually happen, and you won't have to change anything to your code to gain speed from this optimization. Just recompile with a newer version of Zig, and boom. Just a warning, there is something called ziphash, and ziphash is not a hash function, in spite of the name. This is actually a MAC, because if you know the key, it's easy to compute an input that will produce this a specific result. So it's not collision resistant. So this specific function was specifically designed for hash maps. For example, for a hash map, if the input is not trusted, an attacker can craft specific input so that everything ends up in the same bucket. And then your hash map is going to be super slow. So if you use ziphash with some secret key, it's going to be much, much harder for an attacker to actually target a specific bucket. The same thing applies to Bloom filters, count, min, sketch, and all these structures requiring some hash functions. So this is why ziphash is not in crypto.hash, but it's in crypto.auth. Remember that a little bit before, we had to derive two keys from one. This is what you can do with what's in crypto.kdf. You can see an example on the top. You start from a key, and that key can have any length. And all the bits don't even have to be uniform. And from here, you extract a key, which is PRK in this case, and then using this PRK, you can compute any number of subkeys. The second parameter is just a description. This is what you're going to use the key for, and boom, you can have as many keys as you want, starting with just one key. Cool. CryptoStream, you just pass a secret key, a nonce, and you get a deterministic stream of gibberish. This is pretty much what we built with the block cipher and the counter mode before, except that it doesn't have to be a block cipher to build this kind of construction. Let's switch to something a little bit more interesting and talk about passwords. Passwords are leaked all the time. And this is not always because websites are hacked. For example, an employee can make a dump of the database with all the customer accounts before they leave the company. And leaks happen so frequently that if you don't know this website, haveibeenpwned.com, check it out as soon as possible. You will be scared. And a common practice is to hash passwords before storing them. Using regular hash functions is quite common, especially if you take a look at the history of the leaks that you can find in the websites we just talked about. But this is pretty much useless if there are not many passwords and they can be brute forced. Passwords have been designed to be easy to type and remember, so they don't have a lot of entropy. And it's very difficult to actually estimate the entropy of a password. It's almost always overestimated because humans are really, really bad random number generators. For example, if you ask a bunch of people to pick a number between 1 and 10, this is the distribution you get. Yeah, it's not really uniform. For some reason, people seem to like the number 7. It's not right in the middle. It's not too much on the left or the right. I don't know. This is weird. But my point is that humans are very predictable. Which is why modern password crackers don't try every single password blindly. They use permutations and Markov chains and neural networks to try what is going to be more likely first. Also, GPUs and ASICs are super, super fast, especially if they have to do the same thing on very large vectors, such as try many passwords at the same time. You can find a lot of passwords from previous leaks. They can be freely downloaded everywhere. And people like to reuse passwords. So if a password has been recovered, well, you can be sure that everybody's going to try this password on different websites, and it's going to have more than one match. So what about the remaining 30%? Well, same thing. You can compute hashes really, really, really quickly these days. So yeah, what can we do? Introducing what you can find, and there is something wrong in my slide. This is not in crypto hash, but in crypto.pw hash. So PBKDF2 is a very simple construction, which is going to recursively apply the same hash function many times, just to be slow. Why? Well, just to make a brute force attack against a password or anything with low entropy slower or more expensive. A more interesting function you can use, which is also not in crypto.hash, but crypto.pw hash, is called bcrypt. This is a cache hard function. It's going to require a lot of random memory accesses. So these are just reads, but a lot of them and in unpredictable locations, which is something GPUs don't like at all. If the whole lookup table fits in the L1 cache of a CPU, this is going to be super fast. If it doesn't fit, it's going to be instantly super slow. So a GPU is going to be usually way faster than a regular CPU for this. And ASICs can do a pretty good job, but it's going to be very expensive. So that's pretty nice. This is how to use this specific function. That's pretty simple. You get a password, which is Zig which is not a good password. And the second parameter is essentially a work factor. So this is going to be how many iterations this function is going to go through. And what you get is a string. And this string is just like text. It's like base 64 encoded. It's not exactly base 64, but it's just some text that you can directly store in a database. And if later you want to verify that Zig is a correct password, you can compare what you previously stored with what has been recomputed for Zig So the API is very simple, just two functions, hash and verify. Okay, let's switch to crypto.sign. This is just a signature system. ED 25519 is a pretty common signature system. It's actually a really good one. If you use SSH, you probably use it every single day. So a signature system is something with a bunch of functions. You can generate a key pair, so a function that returns a private key and a public key. So instead of private key, I tend to say secret key, so that you get PK and SK instead of PK and PK. So once you get a key pair, If you know the secret key and a message, you can compute a signature for the message. And given a message, a signature, and a public key, you can verify that the message has been signed by someone who knows the secret key. So that can be very useful if you want to sign firmware updates or software updates or whatever. And ED25519 is interesting because keys are really small and signatures are small as well. So you can even enter them directly on a command line if you want to. This is really great. How to use that in Zig? Pretty easily. You have a function to create a key pair, a function to sign, a function to verify. So this system is fast and secure unless you have some way to have a fault attack during the computation of a signature. It could be a raw hammer attack, it could be a voltage glitch, whatever. This is not so common, and usually you don't have to care about that. But if you do, as of today, a mitigation which is believed to be efficient is to add some noise, some random noise during the computation of a specific step of the signature. And Zig is one of the rare implementations that allows you to do it. And if you look at the previous slide, when we had the sign function, we had the message, we had the key pair, and the third parameter was set to null. But you can set this to a random, it's not even a key, just some random bytes, and it's going to add this extra protection for you. We also support batch verification. So if you have a lot of signatures you want to check very quickly, this is going to be faster than individual checks. This is great for blockchains. So ED25519 in the original paper has been underspecified. For example, there are different ways to represent the same public key, or different signatures can be valid for the same message. And it's okay for what it was originally designed for. However, applications may have different expectations. So after the research, the original paper and the RFC were published, a bunch of research papers have been published, and implementations have been improving over the original specifications as well. And to date, Zig has the only implementation that achieves both maximum security and maximum features. That's pretty cool. So there's a bunch of things with 25519 in their names, plus some related stuff. I'm not going to talk about them today for a very good reason. This is going to be addressed in a different talk where I will be talking about fast finite field arithmetic in Zig, elliptic curves, and everything you can see here. So let's not spoil it. And switch to crypto.knuckle. You might be familiar with knuckle and tweet knuckle, and you're supposed to say thought, not knuckle, whatever. So knuckle is, or actually tweet knuckle, because this is probably the most popular implementations with Ellipsodium right now. This is a very small library that was published as 100 tweets a couple years ago. And since then, people have been rewriting tweet knuckle in many, many different languages. In particular, in JavaScript, there is tweetKnuckle.js, which is used everywhere because it's very small, very easy to use, and it's a very simple way to have crypto that you can use pretty much everywhere. It's compatible between different languages. It's easy to embed on any application, so it's pretty nice. You can even find it in the Go standard library in crypto.knuckle.blah, blah, blah. And in Zig, we have everything that tweet-knuckle has. So we have all the constructions from knuckle, including xsalsa, which is something I talked about a couple slides before. But what's probably more interesting is the secret box, and seed box constructions. Remember that when you send a message, you need to send the ciphertext plus the tag Plus, if the recipient doesn't know the public key, you need to send the public key. How do you send all these things? Well, whatever you want. You actually can use any serialization format you want, but there's specific formats, secret box, bot, and seedbox do it for you in a pretty standard way. So let's take a look at seedbox, which is something you can find in libstudium and Go. This is an extension to the original Sweet Knuckle API, but it's probably what I would recommend. So this is very easy to use. You can create a key pair. So Joe has now a key pair. Joe KP is a structure with two members, public key and secret key. Now you want to send a message to Joe. That's very easy. You take your message and using Joe public key and the message and the function seedbox.seal, boom, you get a ciphertext. And that's it. Joe receives the ciphertext and he can decrypt it using the secret key. That's it. There's still one thing to pay attention to. When you encrypt something, in addition to the message, you need to reserve some space for extra data, such as the public key and the nonce, which is why you have the ciphertext whose length is the length of the message plus seal underscore length. You don't have to compute details for you. This is exposed as a constant. So very easy to use, and it does everything for you. Some takeaways while I've been working on crypto in Zig. First, result location semantics are great, especially when you have to chain multiple computations. That was very useful for all the elliptic curve arithmetic. Very clear, very nice to read and write. I love this. You know that you can write very readable code without paying some extra cost because of extra copies or whatever. A surprising thing is the inline keyword. If you just trust the compiler, you get pretty good performance. However, sometimes adding inline can completely change the performance of a specific function in a good or in a bad way. Sometimes you add inline and it's going to be twice as fast, which is pretty impressive because I was expecting the compiler to do the right thing, but sometimes it really helps. And sometimes it can be catastrophic. You add inline, everything becomes really slow. So how do you know when to inline and not to inline? Well, I don't know. Actually, to be honest, I've been just trying to inline a function, benchmarked. Oh, okay, no change. Okay, whatever. Let's try to inline something else. Oh, wow, it's faster now. Okay, let's try to inline something else. Oh, it's slower. Okay, so this is pretty much what I did until I found.
Oh no. It happened again.
Very readable and generic way.
Frank, sorry. We lost you again for 10 seconds. You were talking about inlining.
Crap.
Yeah.
Okay.
I think occasionally you get like a more substantial loss of packets or something. I'm pinning this on you, on your connection, not mine, because I see that I am not dropping frames, but it doesn't matter anyway, sorry. You were saying?
Okay, no, this is probably my provider, but okay. Am I back to it?
Yeah, okay. Yes, you are, absolutely. If I can speak with you, then cool. We are live.
Perfect. Okay, so yeah, so inline is definitely something worth trying. It can drastically improve performance or decrease performance. So the only way to know is to try, benchmark, retry, rebenchmark, and see if you can get a happy combination that provides optimal performance. Don't trust the compiler. It usually does a really good job at figuring out what has to be inline and what should not be inline. But sometimes an explicit inline keyword can really help. Also, vector instructions in Zig are really great. You can write some very simple code, which is going to be generic. It's going to work everywhere, so you don't have to use assembly or intrinsics. This is really nice. However, whereas so far in the implementation I vectorized on x86-64, it provides a great speed improvement. When I benchmarked the same code on ARM CPUs, it was actually slower than generic implementations. I don't know why at this point, and I haven't had the opportunity to try vectorized implementations on other CPUs as well. So what you have in the crypto right now has vectorized implementation just for Intel CPUs. For the rest, this is something I have to investigate. Zig is a great language for crypto. It has a lot of really nice features. One of the things I really liked is the fact that it does checked arithmetic, which was really useful to debug some of my code. That's really cool. But most importantly, the community is awesome. When I discovered Zig and I saw that it had some crypto, I submitted a very small pull request. I don't remember what that was. Just a tiny bug fix, whatever. And I got some really, really nice feedback, and my PR was merged right away. I was like, wow, that's cool. Let's try again. So I sent a different PR, fixing something else, I don't remember what. And same thing, I got a lot of very constructive feedback. And that was great because I was totally new to the language. So it was definitely useful. And PR was merged. So I was like, okay, so this is why I kept sending more PRs. And this is not just because of the language itself, but also because of the community, which is very, very, very nice. Special thanks to people who took some time to review my PR and help me. Terminator, Vexu, Firefox, Lemonboy, KubeCon, Rocknest, Dadaman, Andrew, of course. I probably forgot a lot of people. You're all awesome. So, of course, special thanks to you as well for watching this talk to the end. And thank you. Now, if you have questions, go ahead.
Awesome. Thank you very much, Frank. Give me a second to switch to the Q&A view. Okay, there we go. That was awesome. So thank you very much. Actually, let me give you also a particular thanks from my personal point of view, because not only you covered what you contributed to the standard library, but you also went through the effort of writing a proper introduction to how to use all these cryptography tools. So thank you very much. I've been trying to give myself talks, or in general trying to produce stuff also for maybe not necessarily newcomers, but people that are approaching a particular subject for the first time, and who might appreciate more a presentation that gives them a ramp up rather than just throwing at them the advanced stuff right away. So thank you very much again.
Yeah, no problem.
Okay, so while people start thinking about questions, by the way, if you want to ask a question to Frank, you can write it on Twitch chat. Discord is fine too. Same with IRC, in case you don't have nor want to have a Twitch account. Just remember maybe to tag me so I don't miss the notification. In the meantime, while people start typing, let me ask you, Frank, the usual ceremonial question of how did you discover Zig, and how long ago was that?
So I think that was on Hacker News. It was a blog post about Zig being a better compiler, better C compiler than C compilers. So I just tried it to compile C and nothing else. And I was like, okay, this is cool, nice project. I didn't try Zig as a language itself. But yeah, I was aware of it. And many months later, actually, I was just looking around at what was on my SSD, and I found this directory called Zig. And I was like, okay, before removing this directory, let's give it a try for real. Try this language. So I did, and I was like, wow, this is cool. I love this language. And I kept looking and I saw that it had some crypto. I was like, okay, even better. So yeah, this is pretty much how I discovered Zig.
Awesome. So you mentioned that you were trying to, so you use Zig to compile C, which also brings me to, if I remember correctly, libsodium is implemented in C, right?
Correct, yeah. And some
So
assembly, yeah.
why did you decide to go with C and not C++?
Because I'm more familiar with C, because it compiled faster, because when I tried C++ and Boost, I got error messages that were quite long, to be honest. Like when you try to use templates, this is just terrible. So I was quite discouraged. And yeah, and I think that most of the crypto written in C has never been ported to C++. People tend to use C more. I don't know why. Yeah.
Okay, let's see if we have a couple. We have a couple of questions already. So the first one is, well, it's from Tim Bolt. So nice talk. So they're complimenting you, and then they ask, might remove some deprecated algorithms like MD5. So I guess they're asking you, why did you include deprecated algorithms, and if it wouldn't be a good choice to remove them.
Okay, so first I didn't add them. They were already here when I discovered Zig. And one of my first PRs was actually not to remove them, but to move them to a different namespace, legacy or something like that. And then I got a review from Andrew saying, hey, no, we absolutely need these algorithms. They are not legacy. They are used in real applications, which is actually the case. For example, for the dwarf debug format, you need, I don't remember which one, MD5 or SHA-1 or whatever. So yeah, for any new applications, they're not a good choice. You should avoid them. We have much better as today. But for existing applications, you may still need them. So they're still around and they will stay.
Right. So another question by GW1. How does the speed of these algorithms in Z compare to other languages?
So as of today, my priority was to have a stable and nice API. It wasn't specifically on speed. So everything has been designed to support multiple implementations. For example, if we want a vectorized implementation specifically for AVX2, AVX512, whatever, we can have that. So the priority was really the API. That being said, it's pretty nice so far. It's totally acceptable. If you look at specific primitives such as edges, the implementation we have is just as fast as the one in Ipsodium, which is very nice. If you take a look at all the 25519 arithmetic, it's pretty fast, almost on par with other implementations in C and Rust as well. So that's pretty nice. And for the rest, especially for all the heads and trim ciphers, it's not as fast as it could be, if only because right now blocks are encrypted one at a time. This is totally intentional. It was just to have some initial implementations, once again with a stable API. And then the plan is to extend what we have with the ability to process multiple blocks at a time. But for application, this is not going to change anything. Your application is going to be faster just by recompiling with a new Zig version. So there is a plan to go just as fast as other implementations. It's not done yet, but the plan is pretty clear. And really, even as of today, performance is not bad. If you want to have actual numbers, there is the benchmark.zig file, which is a very small application that's going to run a bunch of benchmark for everything we have in crypto. And you know how many signatures per second we can do and how many encryption we can do, and you get all the figures. And it's really pretty good so far.
Awesome. Yeah, I think that you touched upon a point that I guess multiple people are independently moving towards, and by that I mean, going back also to the question from GW1, I think we are all contributing to the standard library with that same approach of trying to understand the API, trying to structure a subsection of the standard library, even though maybe the API for some things that are more complicated might not be even final, but you try to start approaching the problem from a structural perspective, and then hope that over time people will hopefully maybe even independently contribute parts of the implementation over time. Like that's what is happening, for example, with the async await stuff, the event loop stuff.
Yeah, absolutely. This is exactly the same thing for crypto. Yeah.
Let's see, other questions from Joachim. How have you benchmarked the speed on ARM CPUs? On which type of machine, etc.? Was it ARM 32 or Arch 64?
So this is Arch 64. I have a pretty nice router, not right now because I'm not at home, but at home I have a router with a very nice Arch 64 CPU. And what's interesting about it is that even if it's my ISP's router, you can run virtual machines on it. So I have a bunch of Linux distros running on it, and I can run benchmarks. So it has all the crypto extensions. So this is where I run my benchmarks. And more recently, I got the DTK, which is the Apple ARM development kit. And I run some benchmarks on this new hardware as well.
Great, right, and it also makes total sense that you want that type of stuff to run faster on routers. Now that I think about it, now that you mentioned that type of machine.
Yeah.
Let's see, more questions. Any thoughts on quantum resistant crypto? I've heard Intel has been working on that recently.
Okay, so first, for all the symmetric primitives, hashing, encryption, you don't have to care much about quantum computers as long as the keys are large enough. If you use 256-bit keys, you're safe. You don't have to change anything. So we are ready for all the symmetric stuff. Nothing to change. This is cool. However, for asymmetric constructions, for key exchange and signatures, right now, if we ever manage to build a large quantum computers, the security of all the schemes we use today and the schemes we have in Zig is completely broken. However, we don't know if it's going to happen. If it does, we don't really know when. And I feel like we still have plenty of time to figure out what specific algorithms we want to use. Right now, a bunch of competitions are running. One of them is organized by the NIST, and it's about standardizing the next generation of signature and key exchange system to be post-quantum resistant. The competition is not over yet, so we don't know what kind of functions we will probably use in the future. And even once the competition is over, since all the quantum resistant algorithms really depend on problems that are fairly new, that didn't receive much attention over the few years compared to traditional cryptography, we may still have to wait a little bit before we can safely use them. So if it ever becomes a priority, if tomorrow IBM or whatever releases a large quantum computer and all the crypto is completely broken, yeah, in Zig, we will probably pay attention to existing post-quantum algorithms and probably implement them. However, as of today, this is absolutely not a priority. Even for Lipsodium, this is not a priority because this is not a practical problem. This is more of something so that researchers get some funding. So yeah, if you want to switch to post-quantum algorithms today, you have a price to pay for it. Like keys are going to be large, or signatures and are going to be large, or it's going to be very slow, and implementations are pretty big as well and complicated, and implementations are not that great today. So of course, we have algorithms. We have a problem that's not a really practical problem right now. So probably the best thing to do is to wait a little bit, just pay attention to what's going on. And when we feel like it's time to switch.
Thank you. Just curiosity from me. So do you know what if things have improved from the virtualization point of view? I remember a few years ago, I was like everybody, just buying, so basically renting virtual machines from the usual cloud providers, and I remember that most of them did not have extensions enabled for on the CPUs. Do you know if this has improved?
I don't know actually, and this is something you configure in your hypervisor, and some cloud providers do a pretty bad job at it. Honestly, I don't know. I feel like if you use something like Amazon, you're probably safe. You're gonna have everything available. If you use some smaller provider, maybe not. Yeah.
I see. Here's another interesting question. This is from me, by the way, not from chat.
Go ahead.
Maybe this is a controversial topic. I don't know. I come from the specific angle of ignorance, and I remember reading something about. So you mentioned NIST, right? And
Yeah.
correct me if I'm wrong, but I believe that NIST is this American agency, organization of some kind that basically is sanctions what is good crypto and what is bad crypto, right?
They standardize crypto and they also make recommendations. And yeah, if you want to be NIST conformant, you need to use specific algorithms. Yeah.
Mm-hmm. And I remember reading years ago people being somewhat skeptical of NIST. They were saying that basically NIST would only would have an interest in only saying that what good crypto is actually crypto for which they have a vector of some kind. Opinions on that?
Yeah, of course. Well, tinfoil hat. But still, yeah, the one thing that happened and that made a lot of people skeptical is that among the recommendations they gave, there is a way to build a random number generator using elliptic curves. And these things turned out to be completely broken. So they were recommending a way to generate something very important. This is something you can use to generate secrets. And that thing was completely broken. So people became suspicious. Another thing is that I'm going to talk about it more when we will be talking about elliptic curves. But for some elliptic curves, you need to pick parameters. And for some of their curves, they chose parameters without any justification. They look cool, just use them. But why? How did you come with this set of parameters? We don't know. So maybe this is completely randomly generated and this is safe. Maybe not. We don't know at this point. So people might be a little bit suspicious. However, they also made a lot of really, really good contributions, if only by running competitions. If we have AES today, this is because of NIST. So yeah, if you trust NIST, this is great. If you don't trust them, alternatives do exist. Yeah, but if you have to be standard compliant, you have to trust NIST no matter what.
Right. Okay, that was great. So let me ask you just a couple of final questions, maybe a bit away from crypto, out of curiosity, also for the people watching. And then I think we can end it here, unless more questions pop up in the meantime. So when we had we had a short talk yesterday when we were testing out all the streaming equipment and software, and we were talking about how you got into crypto from but you describe yourself on Twitter as a photographer. Can you tell me, I guess, again, more or less what you told me yesterday about your path into crypto, I think that might be interesting for people.
Okay, so this is two very different things. So let's start with my path to crypto, because this is more on topic. So a while back, I was working on a DNS server, and I was specifically working on something called DNSSEC, which is a way to make DNS more secure, but it's actually terrible. So anyway, I realized that DNS by itself, even with DNSSEC, was not so secure. DNS is great. It's a nice protocol. It works, but it wasn't designed for security. So I was like, okay, what could I do to improve that? So I designed a protocol which is still used a lot today called DNSCrypt. You can check out dnscrypt.info if you don't know about it already. This is a way to encrypt and authenticate DNS. More recently, it can also anonymize your IP address. So this is something I was working on just for fun. I just wanted to solve a problem in DNS. But in order to do so, I had to use some crypto, and I didn't know much about crypto. So I've been looking around for what kind of libraries I could use. OpenSSL looked complicated. And I stumbled upon something called Knuckle by Daniel Bernstein. And I was like, okay, that looks great. That was really state-of-the-art crypto. It was really fast crypto at that time, and it was very nice library, except that it was not designed for application developers. The library itself was not a library. It was just a bunch of C code, and you had to write your application around it. The compilation system was just super complicated. It would only run on the machine it was compiled on. So I looked at it and I was like, all right, I need to improve the code, not the crypto. The crypto, I trust Bernstein for having done something safe, but the code. And once you try to understand the code, you need to understand the crypto behind it. So this is what I started to do. And then I took some online class on crypto, and I got more and more interested in crypto. So I started to read papers, attend conferences, and be more and more involved in the crypto industry. And I started to release more crypto-related code, such as implementations of interesting papers. And yeah, so DNSCrypt became a thing, but besides DNSCrypt, I kept working on crypto, releasing new things and improving libsodium. As of today, libsodium doesn't have a lot of the original code from Knuckle. I rewrote pretty much everything and extended it into multiple things. We wrote a lot of things in different languages, but this is not just about implementation. This is more about the field itself, which is constantly evolving. You were mentioning quantum computers. This is an interesting topic because people got interested into new problems to build crypto on. So this is also what keeps me interested in crypto today. It's the fact that it's constantly changing. So I keep reading papers, talking to people, going to events, and yeah. So this is how I went into crypto. And yeah, your second point, yes, I'm a fashion photographer. You can check out my website. This is prettysimple.images.com, all attached, or my Instagram, pretty_simple_images. This is completely different from my crypto work, but yeah, I'm a professional fashion photographer. You can find me during the Paris Fashion Week and London Fashion Week a lot. I do editorials, I do catalogs, and all these things. So it has nothing to do with crypto, but it's nice to do both.
Yeah, awesome. So I guess we can end maybe with one final question. If you had to give advice to people about photography, one piece of advice, what would you say?
First, don't waste too much money on the gear itself. Just go in a room, walk around, and trying to find the spot where you see the best light. And this is a really good start. You need to pay attention to the light more than you need to spend money on the gear.
Awesome. I think that's really good advice. Coming from somebody that probably spent way too much money on video gear for the people watching. Anyway, thank you very much. Is there anything else before we move forward?
I think we're good. Just enjoy the release party, and you can try Zig 0.7.0 right now because it's an exciting release. A lot of stuff happened since the previous one. So do it and enjoy. And Zig is awesome.
Awesome. Thank you very much. Thank you. Bye, Frank.
Thank you.